So let's recap our goal, right? Our goal is to design an encoder and decoder that allows us to transmit the maximum number of bits per channel use. So basically, we're allowed to use this discrete memoryless channel n times, and in those n channel uses, we want to transmit k bits of information in a way that the final estimate mk hat is such that the decoded signal mk hat is equal to mk with very high probability. So the probability of error of decoding mk is something which is hopefully vanishing as n tends to infinity, or correspondingly as k tends to infinity. Right? So we're right now we're explicitly focused on the case where k and n are growing, right? So it's for very large blocklets. But in practice, you have some target probability of error for a fixed n or a fixed k. Right? So if you can fix n channel uses and a target probability of error, maybe whatever 10 to the minus 3 or 10 to the minus 4, and you want to know what is the maximum number of bits that you can transmit in these n channel uses, where n could be say 100 or 1000 or so. In practice, for example, in 5G communications, the typical bandwidth is the typical block length n is something like 10 to the 4 or 10 to the 5, which is large enough for our purposes. However, there are of course a lot of other applications in 5G itself where delay is a major bottleneck. Think of, say, industrial control of some devices. Right? You want to transmit some signals to devices that control some unit of a plant, and you want to transmit these messages with as little latency as possible. And in such scenarios, you also want it to be very reliable. So this is broadly termed as ultra reliable and low latency communications. So in such scenarios, you want n to be very small, of the order of, let's say, 100 or so, and the probability of error is also required to be very, very small. In these cases, you don't want high rates. The rate is typically something small, but n is small and the probability of error is also very, very small. In contrast, in this particular course, we are basically interested in the scenario where PE is of course very, very small, but n is very large. Okay, that's the regime that we'll be working with. So we want to know what is the maximum rate of communication that we can achieve for a probability of error that is vanishing as n tends to infinity. All right? And remember, we are explicitly interested in this probability of block error. You want the maximum rate.
If probability of error is going to vanish as n tends to infinity.
Correct.
Then rate will tends to 0. Right?
Not necessary. So we want to know if it is possible to achieve a rate that is not vanishing. If we use the repetition code, I agree, it is impossible to achieve a vanishing probability of error and a rate that is non-zero. Right? But the whole point of what we'll try to prove is that it is actually possible to achieve a probability of error that is vanishing as n tends to infinity, but asymptotically the rate is something strictly positive. So in n channel uses, you can send some fraction of n number of useful information bits, right? Maybe n by 2. Okay. Okay. So quick recap about what we saw regarding encoders and decoders. So we'll essentially focus on this form of an encoder. So any deterministic encoder can just be represented as a table. For each message, you write down what is the corresponding code word. So when you want to transmit, say you receive a message of k bits, then you look up that particular row of this table and transmit the code word corresponding to that row. This is the simplest, conceptually it is the simplest encoder that we can think of. It is computationally complex, but let's not worry about it at this point. And the decoder is basically some map that takes the received sequence and outputs an estimate of the source message. All right. We know that among all possible decoders, the map decoder achieves the minimum probability of error. And if the message is uniform, then the map decoder is the same as the ML decoder. Okay. Okay. So now so what is the goal? So we introduce a little bit of notation. So right now, remember, we are not looking at a fixed n, but an n that is growing. All right. So for large enough n, what is the largest rate that we can achieve, such that the probability of error can be vanishing in n. So we'll define the capacity of a DMC is the largest rate, more precisely the right. So we basically want to know asymptotically what is the largest rate R for which there exist codes with probability of error that is vanishing as n tends to infinity. All right. And that largest or supremum of all possible such rates is called the capacity of the discrete memoryless channel. And this is the result that we'll try to prove. So for any discrete memoryless channel, the largest possible rate, largest asymptotic rate that we can achieve is equal to the maximum of the mutual information, where this maximum is taken over all possible distributions on Px. All right. So Px, we'll call Px an input distribution because it's a distribution to the input of the channel. And the maximizer so the Px that achieves this maximum is called the capacity achieving input distribution. So magically, the largest rate that we can achieve is given by a mutual information. And if we think about this result purely intuitively, right? When we say mutual information, it is the amount of information that you get about the input x from what you observe y, right? Now, what does the rate of reliable transmission mean? Basically means that in n channel uses, you are transmitting k bits or nr bits of useful information, which can be reliably recovered, right? So, naturally it would be, we would kind of expect that the amount of useful information that you can transmit in n channel uses would roughly be the amount of information that you can recover about xn having observed yn, right? You can't really transmit, you can't really recover any more bits of useful information than that. Okay, again, this is very much intuitive, just to develop, just to think about it in this particular intuitive fashion. All right, and the amount of useful information that you can gather about xn from yn is basically I xn yn, which is n times ixy, roughly, because it's a discrete memoryless channel. And this is, of course, now this ixy depends on the input distribution, px, right? What is given to you is the channel, which is py given x. And so px is something that you are free to choose. So if you want to maximize the rate or maximize the amount of information that you can send through this particular channel py given x, then that would be maximum overall possible px of the mutual information ixy. Right. So that's the intuitive interpretation about of this quantity, which is the channel capacity. But of course, intuition is not enough. We have to prove that this is actually an operational quantity, and this has some meaning in terms of the reliable rate of communication. The intuition essentially comes from the channel coding theorem, right? So ixy as a measure of information is basically derived from the channel coding theorem, because it means that you can design codes for which you can transmit these many bits of information reliably through the channel py given x. All right? Does that make sense? Any questions?
Sir, when you mean n channel users,
Correct.
single channel being shared by n users, or
No. So there's exactly one transmitter and one receiver, right? But then you can transmit over n time instants. So n time instance is what I call n channel uses, because you think of each time instant as one resource, right? So it's like using the channel again and again and again. It's just a terminology that is prevalent in information theory. That's why we are saying n channel uses. Any other questions? Okay. So let's try to break down what the channel coding theorem is saying. It says that, this coupled with the definition of capacity means that, number one, it is saying that there exists a sequence of codes for which the rate is arbitrarily close to the capacity and the probability of error goes to 0 as n tends to infinity. That's one part. That's by definition the capacity, right? The capacity is the largest rate for which the probability of error goes to 0 as n tends to infinity. And the second, it also says that if you try to operate at a rate above this quantity, above max over px of ixy, then the probability of error can never go to 0 as n tends to infinity. No matter how you choose your encoders and decoders, if you try to operate at a rate above the capacity, then the probability of error cannot be made vanishing in n. Or effectively, what it is saying is that if you have any encoder and decoder for which the probability of error goes to 0, then it must be the case that the rate is less than or equal to the capacity. It can't be any more than the capacity. So first, some remarks. When I define the capacity and rate and probability of error, we're basically saying the probability of error is the average probability of block error, right? And so in principle, maybe the expression for capacity could potentially change if you relax the block error probability constraint to a bit error probability constraint. Because if the block error probability is going to 0, then the bit error probability definitely also has to go to 0, but not vice versa. You could have a code for which the bit error probability goes to 0, but then the block error probability maybe doesn't go to 0. So if we relax the block error probability constraint to a bit error probability constraint, then is it possible to achieve a higher rate? Or does the capacity increase if we go from a block error probability constraint to a bit error probability constraint? It turns out that for a discrete memoryless channel, it doesn't. All right. So for a discrete memoryless channel, the capacity is the same if we replace the probability of block error going to 0 with the probability of bit error going to 0. All right. And again, one thing to note, that this happens if the channel is a discrete memoryless channel. If the channel is not a memoryless channel, then maybe the capacity is different for under probability of bit error going to 0 versus probability of block error going to 0. They could be very different. All right. In fact, not just so, the bit error probability is a relaxation of the block error probability. But then you could also demand something even stronger, which is called a maximum probability of error constraint. Yeah. Okay. So basically, now we have this discrete memoryless channel, and we said that the capacity, or basically we're looking for the largest rate of reliable transmission, where reliability is measured by probability of block error. All right, so the whole message should be recovered exactly. Not even one of those bits can be in error. Right? Under this requirement, the maximum rate of transmission is equal to this particular quantity. The capacity is max overall Px of Ixy. Now, suppose I relax this. I'll say that I don't want the entire block to be recovered correctly. All I want is the bit error probability should go to 0. Okay, which is a weaker requirement than the block error probability going to 0. Right? But it turns out that even if under this weaker requirement, the maximum rate of reliable transmission is still equal to the same quantity. Okay, and this happens for a discrete memoryless channel. If the channel is not memoryless, then I don't give this guarantee. It could be the same, it may be different. Okay. And in fact, it also is true if you replace PE with the following, which is max over all possible messages of the probability so this is sometimes called the maximum probability of error, while this PE that we defined earlier is sometimes called the average probability of error. Okay, so the point here is that when you take the maximum probability of error, or when you take the average probability of error, what is that equal to? It is equal to summation over all possible messages times of the probability that the decoded message is not equal to the true message, given that this particular message was transmitted, times the probability of error times the probability that that particular message was transmitted. All right. Now, under this average probability of error, maybe you have designed a code where if you transmit the all zeros message, then you'll always be in error. Whatever, it's a weird code that has this particular property. Okay. And maybe all of the other messages are recovered exactly correctly. Okay, it's a very hypothetical scenario where the all zeros message is always decoded incorrectly, whereas all of the other messages are always decoded correctly. It's maybe not a DMC, but some channel and some code. Okay. Now, under this scenario, what happens to the average probability of error? What can you say as k tends to infinity? As k tends to infinity, the average probability of error will go to 0. Correct? But what happens to the maximum probability of error? What would be the maximum probability of error? It's 1. Right? So, it is possible for a given code could have a very small average probability of error, but the max probability of error could potentially be very large. Right? One thing is straightforward. The maximum probability of error is always going to be greater than or equal to the average probability of error. And this quantity is always going to be greater than or equal to the probability of bit error. So these are all weaker requirements. Definitely if this goes to 0, then both of these go to 0. But just because this goes to 0 doesn't mean that either of these should go down to 0. Okay. But it turns out that even if you impose a much more stringent requirement, that is, the max probability of error should also go to 0, even then the capacity still remains the same for a discrete memoryless channel. Okay.
So what is the difference
Okay, sorry. It should have been M superscript K. Right? So little m superscript K is a realization of the random message capital M superscript K. Any other questions?
So can you define maximum probability?
I'm sorry?
Can you define maximum probability?
So this is the maximum probability of error. If you want a more explicit description, this is summation over all possible max over all possible messages right of the probability of error, which is summation over all yn such that the decoding of yn is not equal to the transmitted message nk of p yn given xn of yn given the encoding of mk. Right? So this is basically, this quantity is the probability that there's an error because this particular message was transmitted. So given that this particular message was transmitted, what is the probability that that message is decoded incorrectly? All right? And you take the maximum, the worst case message that can possibly be transmitted. In contrast, for the average probability of error, you take the average over all of those conditional probabilities of error for each possible message. Right? Yeah, there was another question. I'm sorry, what do you mean?
When does the maximum probability of this go to 0?
Can you elaborate a little bit?
This Pmax, like in what condition will it go to 0? Like you mentioned before that if Pmax goes to 0, then P and Pb goes to 0.
Correct.
So like in what case will that happen?
It depends on how well you design your code. Right? If you don't design your code well enough, then it's possible that the maximum probability of error doesn't go to 0. So it's difficult for me to say when it will go to 0. But for example, let's take a dumb code where two messages are mapped to the same code word. All right? For whatever reason, you design the code badly. So this means that for that particular, for that pair of messages, it's impossible to distinguish between them. So one of those messages is always going to be in error. All right? But then maybe this collision happens for only one pair of messages. And so the average probability of error maybe goes down to 0. But because of this collision, the maximum probability of error would not go down to 0. All right? So, for example, this could happen when there's some subset of code words which are very close to each other. Close, again, it's a very loose term. All right? Does that at least partially answer your question? So, again, in the interest of time, I won't go into it in too much detail. But as it turns out, if you have a code, what you can show is that if you can construct a code of a certain rate for which the average probability of error is small, then you can also construct a code for which the maximum probability of error is small. And you can do that by throwing away some of the code words. So if there are some code words which are very close to each other, then you throw away some of those code words so that there are no code words that are sort of close to each other. Right? Again, this is sort of a very intuitive description. But again, we'll mostly be interested in this average probability of n. All right. If you're interested in knowing more about this, you can look up the Cover and Thomas textbook. It has a small discussion about this maximum versus average probability of error. All right. Any other questions? Okay. So, for a discrete memoryless channel, right? Let's try to look at the asymptotic probability of error for the best code of a given rate. Okay. So basically, what I am doing is let's increase the rate from 0, and what is the maximum possible rate of transmission I can have for a given channel? I'm not talking about the reliable rate of communication, but maximum possible rate. In n channel uses, assuming that the channel is perfectly clean, how many bits of information can I transmit? So when I say a channel, I'm saying that there's a specific channel input alphabet and a specific output alphabet. And I'm assuming both of them are finite. What is k? Yeah, what is the maximum number of bits that I can transmit? But that assumes there's a distribution, right? So, assuming that, let's go back to this particular channel, right? So, this is a model for a channel. There's a fixed input alphabet x, output alphabet y, and a py given x. Let's say I didn't worry about the probability of error. I don't care what the probability of error is. What is the maximum number of bits that I can ever possibly send in n channel uses? Let's further assume that py given x is a clean channel. All right, this is absolutely, let's say y is equal to x with probability 1. Then what is the maximum number of bits I can transmit? Yeah? Why 1?
K is log cardinality of x.
Correct. So basically it's log cardinality of x, right? Because I've not assumed anything else. I haven't assumed that the input alphabet is binary. So the maximum possible rate that you can achieve is log of cardinality of x. Not any more than that. So for any channel with an input alphabet x, the maximum possible rate can be log cardinality of x. It's impossible to transmit at any higher rate, right? So I have a rate on the x-axis, or the asymptotic rate on the x-axis, and for this I have the minimum possible probability of error on the y-axis, asymptotic minimum probability of error. So for every rate r, I choose that code which achieves the minimum possible probability of error, and I look at this quantity as n tends to infinity. Okay. And here I have the capacity, that's sort of a threshold. All right. What does the channel coding theorem say? If R is less than C, then what can you say about PE star? Yeah? It'll be 0, right? Because I'm talking about the asymptotic probability of error. So if you are operating at a rate below capacity, then the asymptotic probability of error goes to 0. Right? So below capacity, the probability of error is basically equal to 0. What happens above capacity? So if you operate maybe at a rate that is slightly above capacity, it can never be 0, I agree, yeah? But what do you think would happen? Would you imagine that the probability of error, the asymptotic probability of error is something that grows linearly or quadratically, or just a guess at this point? I'm sorry? Okay, exponentially increases. Any other guesses? How would the behavior be? What happens as you just go above? You're close to capacity, but you're slightly above capacity. Is the statement clear? I mean, or question clear? So, suppose I take an R that is slightly above capacity plus 0.00001, and I want to know what is the minimum possible probability of error that I can achieve for large n.
K times bit error probability.
I'm sorry?
K times bit error probability.
Oh, then what is the minimum possible bit error probability that I can achieve? Right? Okay. For a discrete memoryless channel, you have the following phenomena. Below capacity, the minimum probability of error is 0, asymptotic probability of error is 0. Above capacity, the minimum asymptotic probability of error is 1. All right, so there's a sharp jump. Again, this is a phenomena that is observed for a discrete memoryless channel. So people sometimes say that discrete memoryless channels satisfy what is called a strong converse. If you try to operate at a rate above capacity, then it's not just that the probability of error is non-vanishing, the probability of error goes to 1 as n tends to infinity. So for a discrete memoryless channel, if the rate is greater than capacity, then for every code, the probability of error tends to 1 as n tends to infinity. And again, I can replace this probability of block error with probability of bit error as well, and that will also tend to 1 as n tends to infinity. So really, if for large block lengths, as soon as you go above capacity, there's really no hope. All right, you can't really get any useful information out of it. And remarkably, as soon as you go just below the capacity, the probability of error can just sharply goes down to 0. So there's really this threshold phenomena that is happening. All right. Any questions?
When you mean asymptotic relation, what it does it mean?
So I'm just saying that I'm taking n to be very, very large, or correspondingly k to be very, very large. So if I take n very large, then below the capacity, for the best code of a given rate, the probability of error will be very close to 0. If I operate at a rate even slightly above capacity, then for large n, the probability of error, for the best possible code at that particular rate, the probability of error will be very close to 1. So there's a sudden jump in the best possible performance when going from rate below capacity and to a rate that is just above capacity. All right. And this sort of phenomenon is something that you see in physics, right? Do you know what the analogy is? Do you see such a threshold phenomenon happening? Sorry? Why? Something even more basic, right? Something that you observe in daily life. No, something even more basic. Basic physics. No. So below something, the property of an object completely changes, and above something, again, don't think about electrical phenomena, because even in a diode, it is not, okay, you're talking about an ideal diode where there is a change, but yeah? How? Okay. So something, again, you don't have this phenomena, right? It's 0 below something and 1 above something else. So this is similar to what you observe at the boiling point or the freezing point of a particular water, for example, right? If the temperature is above 0 degrees, then it's a liquid, right? But as soon as you go below 0 degrees Celsius, it's suddenly the state of matter itself suddenly changes from liquid to solid. So this is also what happens at the boiling point. Right? You can be arbitrarily close to the boiling point, but below, again, we're assuming, like, let's say, constant pressure and all of those things. But below the boiling point, it's liquid. But as soon as you go above the boiling point, it suddenly becomes a gas. All right? So this sort of phenomena is similar in that particular sense. All right? And in fact, there's also this relationship goes far beyond just this, also in terms of the connections between coding theory and physics. All right. Okay. So let's now try to prove this channel coding theorem. So what we want to show is, if we operate at a rate below the capacity, or arbitrarily close to but below the capacity, then we can design codes for which the probability of block error is vanishing in n. And we also want to show that if we operate at a rate above capacity, then it's impossible to achieve a vanishingly small probability of error. Okay. So let's start with the converse part. Where we want to show that if the probability of error goes down to 0, then the rate must necessarily be below capacity. Okay. And the converse will use the same kind of ideas that we have been using in the past, both for the fixed length lossless source coding theorem, as well as the lossy source coding theorem. The idea is always the same. You start with the rate, you express the rate as an entropy, and from the entropy, you use some inequalities, maybe Fanos inequality and so on, to express that entropy as something that is close to a mutual information. And then we know that the maximum mutual information is equal to the capacity. So that's how you get a particular bond. That's a high level idea of deriving this converse. So let's do that. So as always, we'll start with K, which is n times R. So the first step is always to express this as the entropy of something. Okay, what is that something? It's the entropy of the message, because we've assumed that the message is uniformly distributed. All right. The next step is to somehow bring in a mutual information. Okay. And remember, what are the requirements? We want to connect the rate with the probability of error. And the only way we know how to bring in a probability of error through information inequalities is using Fanos inequality. All right. So we'll write this as h of mk minus, I'll add and subtract h of mk given mk hat, the estimate. The first term over here is just the mutual information between mk and mk hat. And the second is the uncertainty that is left in the message given the estimate. Now I can use Fanos inequality. What does Fanos inequality say? So what does Fanos inequality say? The entropy of x, conditional entropy of x given x hat, is less than or equal to the binary entropy of the probability of error plus the probability of error times log of the cardinality of the input. Cardinality of mk is basically 2 to the k. So log of 2 to the k is just k. Okay. So this h of PE plus PE times k is something that's very small. It's much smaller than the left hand side, which is k. All right. But I now still have the mutual information between mk and mk hat. My next step, so ultimately I want to bound the right hand side. Let's try to think about what we want to show. Right? What we want to show is that asymptotically k should be less than or equal to n times the capacity, or it is effectively n times the mutual information between xn and yn, or n times the mutual information between x and y. Okay, that's the goal. But now what I have at this particular point is that k is less than or equal to the mutual information between mk and mk hat plus something that goes to 0 if the probability of error goes to 0. So now from this, how would I get a mutual information between x and y? What do you think the next step should be? What can I use? Very good. So we can use the data processing inequality. So recall that mk, xn, yn, and mk hat is a Markov chain. Right? So if it's a Markov chain, then basically the mutual information between xn and yn is always going to be greater than or equal to the mutual information between mk and mk hat. So k is less than or equal to the mutual information between xn and yn plus this other term, which is the binary entropy of the probability of error plus probability of error times k. Right? Now at this point, I still can't say that I xn yn is less than or equal to n times the capacity. I can't say that directly at this point. So I somehow need to make use of the fact that the channel is a discrete memoryless channel. I need that particular property.
So one second, can you repeat the first one?
Okay. Which point?
Last.
So up to this point it is okay, right? So basically, the first observation is that mk, xn, yn, mk hat forms a Markov chain, right? Because given xn, the yn is independent of mk, and given yn, mk hat is independent of xn and mk. All right? Because this is a deterministic operation, it's the decoding operation. This is also a deterministic operation, it's the encoding operation. And this channel only takes xn as input and outputs yn independent of everything else. All right? If it's a Markov chain, then I can use the data processing inequality. It simply says that mutual information between xn and yn is greater than or equal to the mutual information between mk and mk hat. That's all that I have used here. The next step is to break up I, xn, yn somehow in terms of the individual components, I, xi, yi. That's what I want to show. I want to show basically next show that I, xn, yn is always less than or equal to summation of I, xi, yi for a discrete memoryless channel. So this is equal to, okay, let's do it step by step. I have h of yn minus h of yn given xn plus the remaining. So let's use the chain rule for this particular quantity. In fact, let's use the chain rule for both terms. I equal to 1 to n. H of yi given yi minus 1 minus h of yi given xn and y1 up to yi minus 1 plus h of pe plus pe times k. Now I'm going to use the fact that this is a discrete memoryless channel to say that h of yi given xn and y1 up to yi minus 1 is equal to h of yi given xi. Alright. So this is equal to summation I equal to 1 to n Okay, nothing else. I've just used the property of a discrete memoryless channel. Next, I claim that this is less than or equal to summation I equal to 1 to n h of yi minus the remaining, which is theorem xi plus h of pe plus k times p. Why can I say this? Yeah, so conditioning cannot increase entropy, right? It can only reduce entropy. So this is equal to summation I equal to 1 to n of the mutual information between xi and yi plus h of p plus k times p. Why is this true?
Plus it is the maximum.
Because by definition, C is equal to the maximum of Ixy over all possible Px. Right? So for each of these Ixi, Yi, the Py given x is the same, right? Because it's the same channel that you're computing the mutual information of. But then Pxi could potentially be different. All right? But then C is the maximum over all possible such Px. So C is always greater than or equal to Ixi, Yi. So this is just n times the capacity plus h of Pe plus k times Pe. So effectively what I have is that k is less than or equal to n times C plus h of Pe plus k times Pe, or k into 1 minus Pe is less than or equal to n times C plus h of Pe, or k is less than or equal to k by n, which is r, is less than or equal to C by 1 minus PE plus h of PE divided by k times 1 minus PE. I'm sorry? N times 1 minus PE. So as n tends to infinity, if we want the probability of error to go down to 0 as n tends to infinity, then this is 1 minus little of 1 plus something that vanishes as n tends to infinity. All right, which is basically the capacity. So if we want the probability of error to go down to 0 as n tends to infinity, then the rate must be less than capacity. Right. No matter what you do, you can't operate at a rate above capacity and still have the probability of error to be vanishing in it. Another way of restating the last statement would be the following. So we have k times 1 minus PE less than or equal to n times P plus the binary entropy of PE. Now the binary entropy is always less than or equal to 1. Right? So this is less than or equal to n times the capacity plus 1, or 1 minus PE is less than or equal to C by K by N. I've divided both sides by K plus 1 by K, or PE is greater than or equal to 1 minus C by K by N, but K is N times R. Right? So it's 1 minus C by R minus 1 by K. So this is saying that, and again, so one thing that you have to keep in mind is that in all of these steps so far, as we went through a sequence of steps, we didn't really assume that n is very large or anything of that sort. This holds true for every n, for every encoder. All of this is just based on standard information theoretic inequalities, and it holds true for every n. So for every n, the probability of error is always guaranteed to be greater than or equal to 1 minus C by R minus 1 over K. All right. So if you're operating at a rate that is above capacity, so let's see what happens. If the rate is below capacity, then this quantity is something that is greater than 1. All right. And for large enough K, the whole right hand side would be something that is less than 0. So this statement isn't giving you anything useful. It's just saying that the probability of error is greater than or equal to a negative quantity for large enough K. Not useful. But then if you're operating at a rate above capacity, right, then this quantity is strictly less than 1. Let's say that you're operating at a rate that is, such that C by R is, say, 0.1. Okay, or maybe C by R is 0.9. Then it means that the probability of error is always greater than or equal to 1 minus C by R. So asymptotically, this is guaranteed to be greater than or equal to 1 minus C by R. So if the rate is above capacity, then the probability of error will be above 1 minus C by R. Right? Now this is something, the behavior that is predicted by this inequality is a little bit different from what I actually stated over here. So in this case, I said that if you operate above capacity, then the probability of error suddenly jumps to 1. All right? But this lower bound is weaker than that. All right? It only says that this is greater than or equal to 1 minus C divided by R, which basically means that it grows whatever, something like so C by R, so it grows sort of something like this. So it's still below, it's a lower bound, remember, and this lower bound is not necessarily tight. But what it definitely says is that the probability of error is definitely above 0, not necessarily tending to 1. Any questions? Questions? Okay, so let's have a quiz. Yeah. Here R should be, if R is less than C, then what happens to the right hand side? It becomes negative, right? So then this doesn't give you anything meaningful because you know that the probability of error has to be greater than or equal to 0. So it's not a useful inequality if R is less than C. But if R is greater than C, then it says that the probability of error can never be equal to 0. It has to be greater than 0.